last but not least, we've got exponential models of differentiable functions. So basically, this is putting to practicality, putting into the real world our new skill of finding the solution to a differentiable function. The main way we do this is through this stupid equation that's never going to leave. It's here forever, basically. Um, sorry, I immediately got negative. Anyway, this is a way of mathematically saying that the rate of change is proportional to y. So saying that the rate that something is changing at, the slope or whatever, is proportional to y. Meaning that the slope and y have some kind of relationship. We don't know what exactly the relationship is unless we're told. So we define this relationship as k. It could be inverse, it could be direct. We don't know. We just know that's k. Well, sorry, we don't know, but we can still represent that we know that there is a relationship with k's inclusion in this equation. Um, and basically, you're going to be told, like verbally in every single problem, the rate of change of blank is proportional to blank. And that's how you're going to find out that you need to use this equation. For example, in this, which we'll come back to this problem later, but let P of t represent the number of students in a school who buy their lunch after t weeks. Suppose P is increasing at a rate proportional to 600 minus P. So increasing at a rate, dp over dt probably, proportional, k is proportional to 600 minus P, which is what y would be in that situation. That's how we're going to be told that we need to use not necessarily even use this equation, but use an equation that has the exact same structure as this. And if this is true, then we know that the function must be an exponential function. Exponential growth or decay it will be this. Now, because we have to use this equation so much, it's also vital that we understand how to use change of wait. Okay, how we have to be able. It's vital that we understand how to solve it, how to find the solution using the earlier methods. And so, because we're going to do it so much, I'm going to go over this final, well, not necessarily final, but go over this general solution for any problem in this thing, basically. So I'm going to separate my variables and then integrate. When we do that, we get ln absolute value of y equals at plus c. Now, to get rid of this ln, we're going to take it to the e. Still don't know if that's how you say that. That's going to cancel out. We're going to get y equals e to the kt plus c. And remember what I said earlier about how e to the kt plus c is the same as e to the kt times e to the c, because of the fact that this is just how exponentials work. This is one of the properties of exponential functions that we learned in algebra 2. But I also said that e to the c is equal to c because any number to the power of a constant is still going to be a constant. So we can say y equals c e to the k t. Is a function, or yeah, that is a function that you are going to be seeing a lot. This is a general solution that is never going to go away, ever. Here it is here. The exponential growth and decay model theorem, as they call it. It's this thingamabob. Now let's go about putting it into some practical use. All right. I already have this circled. Sorry, I tried to record this video a little bit ago and I was like falling asleep while I was doing it. I don't know what was going on with me, but I was like losing my mind. But anyway, a curve passes through the coordinate point 0, 5 and has the property that the slope of the curve at every point P, the slope of the curve at every point P is twice the y coordinate of P. So in this situation, we're being told what K is. It's twice. The relationship is that this is twice of y. So we can just put a 2 in instead of having to look for k because they told it to us. So now we have to find the equation, and the way to do this is just how you would expect. Same hunky-dory. Is hunky-dory a word? I think I made that. Sorry, I'm skipping some steps because I don't want to do them. Okay, so now when we get to here, which is just through doing the same general solution steps that we've been doing this entire video, we can plug in, just like we were doing for the steps, a coordinate point here in order to solve for c, which is going to be 5, and that makes our answer equals 5e to the 2t. I think I did x for that, but no worries, it doesn't matter. Okay, moving on to the more complicated stuff. Here is a word problem. Oh, oops. The rate of change of bears in a population is directly proportional. The rate of change of bears in a population is directly proportional to 350 minus n. Basically just translated that first sentence into the math notation we've been talking about. Time t is measured in years. When t equals 0, the population is 100. When t equals 2, the population has increased to 250. All right, I'm gonna make this. Ooh, whoops. I'm gonna make this out of my way. It's too big. We're gonna have to do a lot of math on this one. Alrighty. So this is gonna involve a very similar setup to. So because this has the same pattern as dy over dt equals ky, it's going to follow very similar pattern and end up having a very similar solution. So basically, if you know how to do this, you're going to know how to do this. Might get a little bit harder, but overall, once you know it, you know it. Ooh. So I'm going to integrate both sides. Now when I'm here, I can plug in my first coordinate point 0, 100, so I can determine what c is. Now that I know what c is, I'll plug that back into my problem. And I'll plug in my second coordinate point. Right now, I'm just continuing to solve for k, to take the natural log in order to cancel out that e there. I just realized very negative here. Sorry, ignore that. But now that I have k, I'm just going to plug this back into my solution up here and find my particular solution. All right, so there you go. There's your particular solution. Now we get to do some fun stuff with it. So first up, find the bear population in 3 years. T is measured in years, so that basically just means that we can plug in 3 for that. So I'm going to do this part on a calculator because you have to. About 287 deer. Bear, sorry. Bears. Find the limit as t approaches infinity of n of t. So you might notice, but because we're subtracting all of this from 350, the maximum number of, oh my god, the maximum number of bears that we're going to have is going to be that 350 number. And as we're approaching infinity on a graph, say we have an exponential function, we're growing because we went from 100 to 250. The population is increasing, so this is an exponential growth function, and that means that we're slowly approaching the maximum of 350. So the limit of t as t approaches infinity of n of t is equal to 350. The next up is the Newton's law of cooling, which states that the rate of change in temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So for this problem, we're going to use the Newton's law of cooling, and it's going to be really similar to what we have been doing. So anyway, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and the outside air. Suppose that a roast turducken is taken from the oven when its temperature has reached 185 degrees and is placed on a table where the temperature is 75 degrees. If R is the temperature of the turducken after t minutes, then Newton's law of cooling implies that d of R divided by d of t is equal to k times R minus 75. to solve the differential equation. What we're going to do is the same thing we've been. So this is going to be ln of 75. And now I'm going to plug in this value here to find out what c is. Okay, so c is equal to 100. We can plug that back into the equation. I think this problem was written, I looked at the homework and there was no, like, the way you find the particular solution is with this information down here. So sorry about that. I don't know why Demario did that. I think it was probably a whoopsie. Anyway, I'm going to use the information down here to figure out what k should be. Finally write down the particular solution, which is 7,510 e to the 130, well, 1 divided by 30 ln 15 over 22 t. Is that. Now, the temperature of the turducken is 150 degrees after half an hour. What is the temperature after 45 minutes? So for this, we just have to plug in 45 into that t there. So 736 degrees. All right. When will the turducken have cooled to 100 degrees? So this one's a little bit more complicated because we're going to do 100 equals 75 110 e to the 130th ln 15 over 22 t, and we're solving for t. So we're going to get 25 over 110 equals e to the ln of 15 over 22, 30t. This is going to end up being 25 over 110 divided by 15 over 22. So that's what our time will be. 25 over 110 is going to be equal to 116.055 minutes. All right, so that's going to be all. Thank you so much for watching. I hope you all learned from this video, and I'll help you out on the test on Thursday. Good luck.